All right, hello everyone. Welcome back. Very sorry I didn't get the chance to make a 100 subscriber special yet. I've been very busy doing various things. Anyway, uh, I guess this is part 2 of my Minecraft Computer Showcase series. Today we are going to be looking at the newest edition, this beautiful little graphical processing unit right here. It's not as much as a graphic processor as it is, really, it's just a binary to binary coded decimal, and binary coded decimal to binary conversion device. Basically, what it does is it takes our number, which is anywhere from like I forget the full number, but it's a really large number. Anyway, it takes our binary number and it converts it into a set of digits. It takes, I think it's like a maximum of 5 digits. Yeah, 1, 2, 3, 4, 5. So it represents each digit with 4 bits of data, because the 4-bit integer limit is 15, starting at 0. So each digit is assigned 4 bits, and it encodes that binary value into this binary coded decimal value, which is easier to display on a 7-segment display panel such as this one. And it uses a device called a shift register, where the values that are being sent into the device are stored in a register that will shift its value along 1 bit every single time it's fired. And so that shifts in, and every single time that a number is greater than, I believe, if it's greater than 5, it'll add 3, which means that we'll never get a number higher than 9 in any one digit. Because, you can't display a number higher than 9 in a single digit. It has to carry over and give us a 10 in the next digit, which is really just a 1 and a 0. So the way it works is it just shifts it along every single time. And every single time it shifts along, it's technically multiplying that value by 2. It's a lot of weird math shenanigans. You can look up the double dabble algorithm if you're interested in learning how that works. So that's our output. Our input functions essentially the same way, except vice versa. So it's not the same way, it's really the opposite way. But that's beside the point. The point is really, we put in a number. Let's push 1, 2, 3. Our input panel here is in binary to save space. So what it's done is it shifts our value along from our input panel. Our input value goes in binary, and that shifts along a special shift register I built. And the shift register sits down here beneath the binary coded decimal converter for the output. And here's our 7-segment display memory. Essentially what happens is we have our values coming in from our input panel down here, and they reach this decoder where they encode for a signal in one of 9 lines. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. So each one is stored in a repeater lock shift register. As you can see, each single one has a repeater lock shift register. And that fires every time we add a new digit from this little rising edge monostable circuit here. So that shifts our value along. And every time the value is updated, it sends that through our 7-segment display memory right here. And what that does is that displays the appropriate digit for that value by using a set of torches and repeaters and stuff. This is really slow, unoptimized design, but I did build it myself. I designed it my own. And so that gives us the number that we've stored in our little shift register out back. And what'll happen next, if we were to submit this digit, this number, this value into our computer, it would encode that value into, so first it would shift that value into the first shift of this binary coded decimal to binary encoder. So that would be in there, and every single shift it would do the inverse of the double dabble algorithm until we have our, let's see, this is our output line. So that output line goes all the way down here to our input. So that shifts into this shift register here. And then when the computer is finished shifting that number into the input register right here, then our value is ready to be sent into the ALU for computations or storage in the registry or the RAM or whatever. I know I said I would finish the hard drive at some point. Unfortunately, I have not gotten the chance to do so. I will show you the improvements I've made, though, in just 1 minute. I'm going to clear our storage register right here. What it does is it really just activates a clock that floods the shift register with zeros, and that just pushes everything out the end, and it's never seen again. Doesn't have any effect on anything. It's probably the most efficient method of doing that, to be honest. And this is the updated solid state drive. I have made some improvements at this point. Currently, we do have our storage controller in place, and this is essentially its own program counter and program memory. It doesn't require an ALU because it's not doing any sort of computation. All the computation is performed down here by this little storage allocator circuit, which finds the first open block when it's storing a file. But everything else, it's really simple. It's essentially the ALU taking instructions, but instead of an ALU, it's a solid state drive. We have our own little program counter here, and we have a bunch of lines of program memory, and it'll activate a specific one every single time it gets a new instruction, depending on the conditions that it's experiencing. For example, we have our read enable line, our write enable line, and our IO device enable line. The current obstacle I'm really experiencing here is I need to figure out a way to get this storage controller to perform a specific subroutine based on the conditions that it's being fed by the IO device controller. Because we have our 3 control lines here, read, write, and enable. And the enable line will be on the entire time that the drive is being utilized, but the read or write lines will only turn on once at the start of the drive usage subroutine. Because, to send multiple bytes of data to this drive, the CPU is going to have to go through multiple steps of instructions to increment whatever counter it's using to find the bytes that it's sending. Point is, this is going to be experiencing multiple CPU clocks. And so on the first clock where one of these control lines is going to be active, it's going to have to jump to a specific subroutine for whatever function it's trying to perform. And I got to figure out a way to do that so that it actually responds to these external conditions in a way that I can control. But unfortunately, my brain's not entirely equipped to handle that. It's very much something that I'm not educated enough yet for. But with a bit more tinkering, I'm sure that it will. I'm sure I'll be able to get it to work. I mean, I did design the storage controller myself, so I got this far. I should be able to get a bit further. The current progress I've made is pretty decent. Again, we have our control input lines, and these 3 pink lines down here are the conditionals. So when both both the actual control line itself and the conditional line are both on, that should send a jump signal to the program counter, hopefully. Our program counter is basically just a CPU counter, but it runs off of the CPU counter instead of having its own clock. I did unfortunately have to get rid of the flavor text on the top that says 64 bytes, 16 files, because that was taking up all the space that the storage controller needs to take up. As soon as I'm done that, I might add back some some flavor. I do have the cute little slap FS emblem there and the letter SSD there, but yeah, I unfortunately did have to get rid of some of the decoration. But so far, this computer's been actually mostly utilitarian. I haven't done much decorating other than the control platform. I do have these, guide markers for reference, but that was only really for building the solid state drive. To recap, the way it works is, depending on what the computer wants to do, read, write, or whatever. If it wants to write a file, the drive just finds the first open block in a set of blocks using this little circuit down here called the storage allocator. And the way it essentially works is it'll store the name of the file and its starting position in the file table, and then it stores the file in the first open blocks it can find. Each block contains a link to the next block in the file, so it's a linked list system, sort of a breadcrumb trail, where the computer always knows what the next block in the file is. It eliminates the need for storing the locations of every single block, because that way you minimize the amount of space being used. Reading file works the same way almost. It just follows that trail of breadcrumbs along and jumps to the next block every single time, and that way you get your your full file. And it fetches the actual first block by reading the file table at the end. So our drive has a total of 64 bytes of data. Yes, 64 bytes. That is not much at all, but I'm working with a pretty large scale here. Can't expect me to be able to store like kilobytes or megabytes. Eventually, I will work on building a 1 kilobyte drive, but I'm gonna have to research some like more compact technology, and I'll have to like stack it double high or double wide. Man, that'll be something. That'll be something else. But that is a project for the next iteration of the computer. Currently, the last few things I plan on adding to this specific computer, Citadel 2, no, Citadel 1. Yes, this is Citadel 1. The next thing I plan on adding is, you see how these input lines that are controlled by the program memory, they do terminate at a forward-facing repeater. What I plan on doing is I plan on extending these lines backwards a little bit and then adding 32 or 64 bytes of programmable program memory. And that information can be stored, it can be edited by the CPU. The CPU is able to store instructions in that program memory by reading information from, say, the solid-state drive. So what that does is that allows us to construct a platform upon which we could possibly use the computer to program its own code. And at that point, it would be capable of running essentially a highly altered form of machine language. It does have its own instruction set architecture, so it won't be able to run anything like assembly, but I can get it pretty close. Because once we have our programmable memory here, we can just address that with the program counter, set up some sort of BIOS or UEFI system in the read-only, and have the rest of it run off of that programmable program memory. And then it loads that program from our solid-state drive based on whatever information is stored in the BIOS. So we could make this computer almost entirely self-reliant. All we would need at that point is a way to intuitively program, say, hex values into this program memory or into the solid-state drive so that we can write our own programs. My thoughts are, for the way we could structure this programming language, is just as a specific character to represent a new line, and I could probably use ASCII for that. And we have our actual storage, our actual instructions stored one at a time, and so every single byte contains one instruction. And then when there's a new line byte, it's assumed that everything before that new line is stored in one single line. The same way that you would have, multiple actual instructions stored in a single line of program memory. That would allow us to compile instructions with, multiple instructions per line that would execute at once, or multiple parameters for an instruction, because, registry reading and registry writing or memory access, that's all controlled using a control line and some variables such as input addresses, because when you're storing something in the memory, you need to know where you're going to store it. Same thing with the registry, or if you're reading something, you need to know where you're looking. So having a new line character to group instructions into lines would allow us to write a really nicely structured programming language that would even allow for conditional statements, which would make it fully Turing complete. The computer itself is already Turing complete, considering it does have conditional jumping and whatnot. It can add, subtract. It is capable of doing essentially anything at this point. The only limitation is the fact that I don't know what I'm doing. But because it has conditional jumping right here, this is actually the conditional module. It's Turing complete. If you look up Turing complete on Wikipedia, it's just a measure of computer completeness that was coined by, you guessed it, my homie Alan Turing. But yes, this computer is actually decently powerful, considering it's that the project is still in its infancy. And I hope that I can eventually, finish up the GPU, slash binary processor, finish up the storage controller, and then introduce the PROM, the programmable read-only memory, and allow for the computer to have its own integrated development environment. So you could actually program things in the computer, and then if I were to add a real GPU, you could probably like program Pong or something, and I don't know. That requires too much math. I don't even know how to program Pong in the real world. Maybe I should actually look into that. Maybe I should learn C. I tried learning C once. It was hard. Oh, another thing I did add. When the solid state drive gets too full, the storage allocator will overflow into a full state where one more byte at the end is activated, and that doesn't actually mean that the byte's open. It means that it's out of space, and that signals the interrupt line. This is the interrupt request line right here, and it uses instant repeaters so that the CPU clock can stop without any further instructions being sent. Because if your computer is requesting an interrupt due to a fatal error and the clock keeps sending instructions, you're kind of in a bad spot there. So you want your interrupt to get to the counter as quickly as possible. So we have our interrupts and request line, and that goes up here. Currently, I have no way of managing interrupts. I know it's really a bad idea to have an interrupt controller without any sort of interrupt handling, but it will halt the CPU if there's no more space left in the solid state drive. And I can link anything into this interrupt request line. That way, anything can really cause an interrupt. The user could cause an interrupt. Any sort of piece of hardware could cause an interrupt. So that's really interesting. I just need to figure out a way to get it to understand where the interrupt is coming from and to respond to it accordingly. I do feel like they would need a lot of extra infrastructure, but I will work on that in the next iteration of the device. Additionally, that next version will include... I know this computer is pretty slow, and the main cause of that, the main thing to blame here, is the fact that there's so many repeaters. And we have these endlessly long data buses, on top of the registry and on top of the memory. And that just slows things down even further. So my idea for the next iteration is instant repeaters. You saw some of them on the interrupt request line. And if I were to use these in more places, I would be able to... the computer would bulk up a bit more, that is true, but the thing is, it would completely eliminate most of the delay present because of these repeaters. So that would speed things up a bit. I would be able to up the CPU clock. Currently, it's kind of slow. But yeah, this computer project is coming along pretty nicely. I am very happy with the point that it's gotten to. And I have big hopes for it in the future. I have big plans. I really hope that I can figure out how to get the storage controller working though. Anyway, thank you very much for watching this update on the computer project. I hope to see you in the next video if there ever is one. I will see you later.